Welcome to the episode F of Debugging TV Frames program. You can type your questions during this episode. If I can't answer particular questions now, I then post answers on the website debugging.tv. So, hello all again. I quickly discuss some topics during this presentation, such as on this list. First, I show you a picture representing raw stack, saved function calls, and resulted execution residue seen from the memory snapshot at any time. Then I show you Xcode project source code I wrote to model execution residue. We analyze a Mac OS X code dump and see no residue, to our surprise. Second, I show you a picture that explains why we didn't see such a residue. And I also show you a modified Xcode project that pushes execution residue down the stack region to avoid it being overwritten, and also we look at corresponding core dump. So this is a picture that represents a raw stack. Arrows that point to decreasing addresses, they represent function calls. And then we have return arrows. So this picture represents also some kind of a stack trace. And also notice that at some point, at some time, we save a memory snapshot, or we have a core dump, crash dump. You see a lightning arrow. So at this point, when we open later this crash dump or core dump, you would see a backtrace. And you would see only yellow function calls. Yellow function calls on stack trace frames. And all blue one will be missing because they are considered to be residual past execution history, and to analyze, to see them, you need to look at raw stack data. So here is an Xcode project. I created some set of elaborate markers. So basically, to avoid typing, what I want to do, I want to create from 5 to 10 function calls. For example, bar, function bar. You see first, for example, we see bar, we call function bar, and this function bar calls, for example, a function bar underscore 1, function bar underscore 1 calls function bar underscore 2, and finally we come to bar underscore 5 that does abort. This is just to trigger call dump. And the same, you see the deeper structure, the deeper call for nested for full function calls. So what we do, if you compile run this application, it creates a code dump because of abort call. So I already created a code dump, so I open it. Actually, there are some warnings. Let's quit. And So let's basically what we do, we recompile, and then we run. Let's create fresh code dumps. So you see that application code dumped, and it's this core. So let's load this core dump. Oh, I'm sorry, something's wrong. Yes, this one. So let's look at backtrace. So we see this backtrace. We see all these bar calls terminated in abort. So consider, for example, that the blue arrows were somehow previous foo calls, and let's see if we can find them on execution residue, on raw stack as execution residue. So what we do, we see what's the value of our stack pointer. So we see this value, but let's dump, for example, 1000 addresses. Let's start, but they remember that stack goes down to lower addresses, so let's start with this address and see if we can find any execution residue left for about 4 function calls. So we get some output, and if we look down, we see some addresses left. Like for example, abort and possible other calls. They may be coincidental symbols, so need to be checked. But here we see only raw stack data that corresponds to our backtrace. Again, I repeat, backtrace. So you see that. So we don't see any foo function calls. This is because they were overwritten most likely by functions such abort and so on. So this corresponds to this absent residue. So suppose that after blue calls, there was another call that is represented by rightmost yellow arrow. And this call, for example, maybe create lots of local variables, local arrays, so, and therefore overwrote previous calls. And so when we create a code dump, we see backtrace, for example, but we don't see any residue because it was overwritten. How can we avoid this overwrite? We can modify our project. What we can do, we can just swap comments to have the same line numbers. So what we can do, we use we define function foo, the first one, as a function that allocates some array, and we specify array size, a macro parameter. That means that when we call this function, all subsequent calls like this would be located deeper down on the row stack, and so there is some chance that they wouldn't be overwritten, remain intact, even after bar sequence calls other functions such as abort, kill, and so on. So let's compile this modified program and run to get another code dump. So let's see. So this is the new code dump. So let's open crash dump. So we see the same backtrace, stack trace. However, so let's dump some portion of stack, row stack. So let's dump the same number and dump say from this low address. So if we continue dumping, we would find our execution residue. We see that foo calls. And now if we continue down, we also have our current backtrace. So I hope this demonstration shows you the importance of this pattern, execution residue, and also the importance of understanding why we sometimes can't see it and why we sometimes see it. So in my presentation that you can download later on, you can find fragments from GDB output and command examples. I also put crash reports. And finally, as usual, our advertisements slide, a few adjustments to current training schedule. For example, accelerated training has been shifted by 1 week in July. It is at this date, starts July 18th, and advanced training, advanced Windows memory dump analysis training has been moved to September. And so, last news, Debugging TV soon joins Demo, Debugging Experts Magazine online version of debugged MZPE magazine, just to make content more lively with pictures, Debugging TV session transcripts, and additional articles. So thank you again for watching this episode. Please later check out the slides and recorded video from debugging.tv, and the next episode should be next Friday. So thank you very much for attending. Bye-bye.